Okay, so welcome everybody to this new seminar series. So my name's Dr. Gemma Sharp and I'm a senior lecturer in molecular epidemiology at the Integrative Epidemiology Unit. And this is the first in a new seminar series on climate change and health. And we've set this up as part of the Bristol Medical School's response to the climate emergency. And we're going to be inviting speakers from across the university and also externally to tell us about their work on the theme of climate change and health. So keep an eye out for future emails from us, and we'll also be setting up a website so you'll be able to find out about future events there. And really we just hope that this seminar series fosters collaboration and inspires interest in this important fast-moving and relatively new area. So without further ado, I'll pass over to Gareth, who's also organising this seminar series with me, and he'll introduce our speaker today.
Hey everyone. Yeah, so I'm Gareth Griffith. I'm a postdoctoral research associate, I guess, in the IEU. I work sort of loosely with Gemma, but we met through this climate change emergency action group. So we're very lucky to have with us today Dr. Eunice Lo from the School of Geographical Sciences. Eunice did a PhD in atmosphere, oceans and climate in Reading and looked at stratospheric sulfur injections, I think, if I'm correct, as a sort of geoengineering solution to climate change. But 2017 joined the University of Bristol as a postdoctoral research associate after submitting a thesis, and worked in the School of Geographical Sciences, which is where we knew each other from, and works across the Cabot Institute for the Environment also. And more recent research works with, I think, Dan Mitchell, amongst other people. I think Dan might even be on the call, combining climate science and climate modeling with epidemiological techniques to study the effects of extreme temperatures and climate change on human mortality. So if anyone has any questions throughout this presentation, I think it's worth saying that if you submit them in the chat, then me and Gemma can sort of try and monitor them, and we'll go through them at the end, if that's all right. We're hoping, I think, if it's all right with you, Eunice, to sort of keep to 45 minutes and have 10 or 15 minutes at the end for questions. So without further ado, take it away. Can everyone see I don't know how you'd even tell me. I'm just hoping that you can all see this heat waves and mortality, past, present and future impacts thing. Yeah, take it away, Eunice.
Right, thank you. Thanks very much, Gareth and Gemma, for inviting me to give this talk. I think it's a great initiative to set up a climate change and health seminar series, because this is a topic that I personally find very interesting. And I think it's also, of course, important to look at the human health impacts, or even not human or animal or environmental health impacts of climate change, because it affects basically all aspects of our lives. I'm particularly interested, or my research focuses on extreme temperature, extreme heat, extremely high temperatures in heat waves, and the impact of that on human health, particularly on human mortality outcomes. So I thought I was going to use this talk to talk about what are the past events that's caused a lot of damage to human health, also the present threats of heat waves to us, and looking into the future in terms of some global temperature targets in the Paris agreements, for example. So I can't move my slide. Right, yes. Okay, so I thought I would start with a graph that looks interesting, and this is a graph I saw on Twitter. It's produced by Neil Kay in the Met Office, and he's a climate data scientist there, and he makes really interesting graphics showing how mainly climate has changed in the world. And this is a lot of different circles, and each circle is a year, and each circle has 12 slices around it, and each slice is a month, and you can see it's basically going from January to December in a kind of clockwise direction, but you can see which month corresponding to which slides on the bottom right corner. So this indicates monthly global mean temperature change from 1851, that's the top left corner, to 2020, that's the bottom right corner. And the color of each slice shows the temperature difference of that month compared to the baseline of 1850 to 1900, the global average temperature. So red indicates warming, and the darker the shade, the larger the warming, and blue indicates cooling, and the darker the shade, the more the cooling effect. So it's a general picture showing that like there's a warming trend in the global average temperature from the kind of pre-industrial times up until recent years. And I think it's interesting to point out that by looking at this graph, since I think 1977, all of the slices have been red compared to this baseline in 1850 to 1900. So as temperatures shift towards higher values, and we know that there's an impact or an association between higher temperatures and health, then it's important to look at what that means in terms of human health. So on the left here is a schematic I took from gov.uk and Public Health England, showing what are the common heat-related illnesses in humans when we're exposed to high temperatures. And basically, a lot of the illnesses are respiratory and cardiovascular, because the human body needs to work harder, basically, to try to maintain our body temperature at a stable value or stable range in order to function. And our body will try to, sweat and also increase blood flow to underneath the skin to kind of increase cooling. But if this there's a limit to whether we can kind of maintain this temperature. And so common heat-related illnesses are heat exhaustion and heat stroke. And in extreme cases, it can lead to death. And on the right here is a graph that I'm going to use throughout this talk, or this kind of graph I'm going to use anyway. And it shows the association between temperature on the horizontal axis and the risk of mortality, or the relative risk of mortality, on the vertical axis. So this graph was made from observed temperatures and mortality counts in London in the past decades of data. And we ran a statistical model commonly used in epidemiology to find this relationship. And so it shows that the kind of minimum mortality risk for London, according to the observations, occur at 19.1 degrees Celsius. And above this threshold of temperature, the mortality risk in humans increases substantially, and the increase is not linear, meaning that at the upper end or extreme end of heat, 1 degree increase in temperature is associated with a much more larger increase in relative risk of mortality than milder warm temperatures. It is also true that colder temperatures are also associated with increased mortality risk. But for this graph, we can see that the slope or the curve is much higher, steeper on the heat side for London. So this is another graph showing the relationship for Southwest England. You can see the temperature at which mortality risk is minimum for Southwest England is slightly lower than for London, but in general, you still see this U-shaped curve with increased mortality risk on the red side, which is the heat side. So outside of the UK, this is another graph for New York City in the United States. Again, maybe even more constrained curve for New York City, showing a similar shape. So in a lot of developed nations in the literature, people have found these kind of curves, and mainly for developed nations because they have the long records of temperatures and mortality for the past to construct this kind of relationship. And So I'm going to base my talk on this kind of relationship in terms of talking about my own research. But first of all, I think I'm going to talk about some historic heat waves and kind of the death tolls of these things in the past. So I just picked out a few heat waves that I personally know of or are quite relevant to us. So basically, historically in 1995, there was a Chicago heat wave in the United States. And I think in one of the July days, the temperature was up to about 41 degrees Celsius. And that caused a few hundred excess deaths of that period compared to other July periods in other years. These estimate is not very certain. So I've seen some reports saying 514 deaths and some goes up to about 800. On the top right here is a photo I found online for that heat wave. And this is a woman who was 101 year old then, feeling unwell and needing help during the heat wave. In 2003, Europe had a big European heat wave. I think temperature reached up to 44.1 degrees Celsius in France. This record held for a long time until 2019, and it was broken by a new record of, I think, 45.9 degrees Celsius, also in France. And World Health Organization estimates that across Europe during the heat wave, over 70,000 people died or excessive. So these are excess deaths in that heat wave. And just to mention, Public Health England estimated that over 2,000 of those occurred in England. And because of that, because of the significant impact on health in the 2003 heat wave, in 2004, Public Health England introduced a new heat wave plan for England, which is still running today, and they update it every year. Just to give a few more figures that I found in a report by the World Health Organization, in 2010, the Russian heat wave, 56,000 people died. And overall, across the world from 1998 to 2017, 166,000 people were estimated to have been affected and died worldwide. So it's quite a grim picture. And a lot of, whenever an extreme event happens, it is very common and logical to ask was this due to climate change? We can't really 100% say whether something is climate change or not, because there's always a chance of just variability playing a role. That natural and internal variability in the climate system does play a role in everything. And so any extreme events could have happened by chance, but we can ask the question of whether human-induced climate change increased the frequency or probability of a certain extreme event happening, or the intensity of an extreme event. And this is often done in extreme events attribution studies. So a paper just a year after the 2003 European heat wave estimated that human influence at least doubled the chance of that heat wave happening. And how they do extreme events attribution is basically they run a trusted climate model under the conditions that actually happened, like such as 2003 over Europe, or the actual conditions, including human influence and also natural forcings or natural factors such as solar activity changes and also volcanic eruptions, and using exactly the same model, exactly the same conditions, but taking out the human factors. Then they run another set of simulations and under those natural only conditions. And by doing this many times, then you have a distribution in each set of experiments shown on the right here. It's from a different paper, but the idea is the same. So say you run a natural experiment, and that gives you a distribution of European summer temperature as the blue distribution, and you run another set of experiments including the human influence, and that gives you another distribution, and say that's the red distribution of summer European temperature. and you know what happened in 2003. So you know what kind of threshold was crossed in terms of temperature, and you draw a line, and here is 1.6 Kelvin. That's temperature normally over a previous period. And then you kind of calculate what's the probability of in each distribution of crossing this observed threshold, and compare the probability in those. And in the 2004 paper, they found that human influence at least doubled the chances of the European heat wave in 2003. A subsequent paper then looked at, and that's the paper that produced this graph on the right here, then looked at how, so what are the chances of the European summer in 2003 happening in a decade before that, so in 1990 to 1999, compared to the chances of that happening in the decade of 2003 to 2012. And they found that just a change in the decade, both include human influence, the chance of that heat wave happening increased 10 times between the 1990s decade and the early 2000s. And they also found that without human influence, so just looking at the natural factors in the world, the chances of these events would have been very low, with a probability of happening just 1 in over 1,000 years. So another study by Dan Mitchell, who is also at Bristol, took a step further to look at event attribution in the sense of mortality. So not just how or if climate change increased the probability of the heat wave happening, but also if human-induced climate change increased the mortality risk during the heat wave. And they found that the human-induced climate change increased the risk of heat-related mortality in central Paris by 70%, and in London by 20%. And they did that by, again, looking at an actual world, a lot of simulations of those, and a natural world without the human influence, and looking at the probability of these, the observed mortality events happening in each of the places. So looking in, well, so I talked about some of the past extreme events. Currently, if you look at just England in the past few years, heat-related mortality is still happening every year. These are some figures taken from the Public Health England reports on heat wave mortality monitoring. So they publish a report about how many heat waves happened officially every year, and the estimates of excess deaths in all age groups in all regions in England during each heat wave. So the rightmost column is the total number of excess deaths in all of the heat waves in a year in all age groups. And 2020, that went up to 2,556. And in comparison, if you remember, the Public Health England figures for the 2003 heat wave was also in the 2000s. So one point to make here is that the third column here is also the total excess deaths during the same heat waves, but only in the age group of people aged 65 or above. And you can see a lot of the excess deaths that happen in come from this age group, and so they are more vulnerable compared to other age groups that are younger. Just to talk about, since I'm talking about the present, just to mention the state of climate in 2020. And I just saw this from a report and a blog post in Carbon Brief, and I recommend everybody to read things that Carbon Brief writes, basically. So globally, 2020 was one of 3 warmest years on record, with the most recent decade being the warmest year. In the UK, it's also the 3rd warmest year in the national series, and this series extends back to 1884. So here's a map on the right from the Met Office showing the just annual mean temperature of year 2020 compared to the 1981 to 2010 period. And red is warming, and we can see a lot of places having been warmed from the baseline. From the same source, they say that, again, extreme event attribution study, or attribution study, they say that without human-caused climate change, a year as warm as 2020 would have a very low likelihood. That's equivalent to happening once every 90 years. But including the actual or human-caused climate change, then the likelihood increases substantially to 56%. That's equivalent to happening every other year. And as we remember from the Public Health England figures, 2,556 people were estimated to have died associated with these heat waves, 3 heat waves in 2020, and these are excluding the COVID deaths. So this is a graph from Public Health England's website, and the 3 boxes are the 3 official heat waves that happened in 2020, and these heat waves were determined solely based on whether temperatures crossed certain thresholds, or whether the Met Office issued a warning in the heat health alert system. So they had, of course, a time series of observed deaths over time, and that's, I think, the black dashed line. And also they would have estimated expected deaths on non-heat wave days. So that's the green line, and they calculate the difference of those two to calculate any excess deaths during the heat waves. For comparison, the COVID deaths are the brown dotted line at the bottom, and again, the 2,556 figure excluded COVID deaths, and I think they identify these deaths by looking at the death certificates of whether COVID was the reason of death, and also by whether the person tested positive of COVID-19 some period before the death. So looking from the past to the present, and then it's important to also look at the future, because as we all know, climate change is happening and is projected to get warmer in the future, with extreme heat events projected to be more frequent and maybe more intense in the future as well. So looking in the future, this is a graph provided by my colleague, Dr. Natalie Lo, who is doing some great work on looking at heat stress in climate models projecting into the future. So these are 2 global maps of trends in near surface air temperature on the left and relative humidity on the right. And these are all trends in terms of changes in degrees Celsius or percentage per decade. And I think this is projected up until 2100 using the newest climate models available to us, that they are called the CMIP6 models. As you can see, on the left-hand side, basically all land regions are projected to warm up to 2100, and this will of course have impact on health, because we know there's an association between high temperatures and health in humans. And she's also looking at changes in humidity, because humidity is another factor contributing to heat stress. So she's trying to combine these two and look at what climate change might mean in terms of heat stress to different populations in the world in the future. So if we talk about climate change, it's impossible to not talk about the Paris Agreement. So this is a global agreement, and that has the main aim of keeping a global temperature rise this century to well below 2 degrees Celsius above pre-industrial levels, and to try to pursue efforts to limit the temperature rise even further to only 1.5 degrees above pre-industrial levels. The United States left the Paris Agreement under Donald Trump, but they rejoined, and they officially rejoined a couple of weeks ago. So it's priority to look at what the 0.5 degree difference between 1.5 and 2 degrees in the future and the current state of climate mean to different natural managed and human systems. This is a graph taken from the special report on 1.5 degree warming from the Intergovernmental Panel on Climate Change. And they list various natural and human systems from, you know, Arctic region to coral reefs, and also they included on the rightmost column heat-related morbidity and mortality. So as you go looking at this graph, as you go up, that's the temperature, global mean temperature increasing from the gray shading being the 2006 to 2015 level, that's just below or about 1 degree Celsius. And you go up, there's another gray line of 1.5 degrees, and even further up is 2 degrees line. And for the color of this bar shows how severe or widespread the impact or risks are thought to be in this particular human system for heat-related morbidity and mortality. So currently, we've passed 2006 to 2015. So that's yellow, indicating that the impacts or risks in heat-related morbidity and mortality are already detectable and attributable to climate change, with, I think, even high confidence. H is high here. And when temperature, global mean temperature goes up, then this color kind of intensifies or gets oranger or redder. That means that the risks and impacts are expected to become more severe and maybe more widespread. Is that true? So I did a study on looking at what the Paris agreements mean for heat deaths, particularly for the US. It's particularly interesting because they weren't, or they left the Paris Agreement at the time this paper was out, but now they've rejoined, and it's great. So I looked at 15 cities in the United States, and they're all drawn on this map here. So what I did was, first of all, to look at the existing relationship between ambient temperatures and mortality risk in each of the places. And these are 3 examples of those cities. Chicago was the place where they had a severe 1995 heat wave, Washington, DC, and Phoenix, and a lot of other places. And you can see these are all, these were all estimated with existing and observed temperature and mortality data, and they are all quite different turning out for each of the places. Particularly for Phoenix, the heat impact is less severe, if you like, the curves upwards to a lesser extent than the other places. And also people are looking like that they're more used to higher temperatures, potentially because of their warmer climate there. So with these curves estimated, and assuming that they don't change in the future, which is a big assumption, but we also don't know how these curves are going to change in the future. So then I projected future temperatures in different global warming scenarios for these cities. And I used climate simulations from the HAPPY project that's organized and managed by Dan Mitchell, and is a project dedicated to looking at differences in extreme events and their impacts between the 1.5 and the 2 degree world. So it's looking at what half a degree difference in the global mean temperature might mean in terms of extreme events and impacts. And I also looked at a new scenario, that's a 3 degree warming scenario, because there was a paper that published earlier, I think a few years now, that looked at the nationally determined contributions by different parties in the Paris Agreement. And parties need to submit these kind of NDCs every 5 years. And the first NDCs that they submitted, if you look at all the unconditional pledges of climate action, a paper estimated that it's more likely that the world might end up in 3 degrees warming, about pre-industrial levels at the end of the century, rather than 1.5 and 2. But since then, I think in 2020, the parties, some countries and some parties have submitted new and updated NDCs. So that might, and the NDCs, the nationally determined contributions within the Paris Agreement, are supposed to kind of ratchet up. The ambition is supposed to go up in terms of mitigation and adaptation as time goes on. So anyway, I looked at the difference between 1.5, 2 degrees and 3 degrees in terms of what the temperatures might be like in these worlds according to climate models, and then what the mortality impacts might be in these cities. So here are 2 maps. The left-hand side is the temperature difference in the some parts of the United States between a 3-degree world versus a 1.5-degree world. The cities are indicated on the map here. And on the right-hand side is between a 3-degree world and a 2-degree world. So 3 degree, 2 degree, and 1.5 degrees are global average warming above pre-industrial levels. But in overland regions and in the places I'm showing here, the temperature difference is often bigger than the global mean difference. So one of the things that I looked at was looking back at the 1995 Chicago heat wave, and one figure that I showed before showed that 514 excess deaths happened during the heat wave in Chicago, and I looked at what are the kind of probability of the same mortality events happening in Chicago under different warming scenarios. So the green is the 1.5 degree warmer world. And I plotted the graph here on the right. So that's basically the kind of the number of heat-related deaths at different return periods. So, and the horizontal line is the 514 observed value. That's a lower range of estimates I've seen online. But I've used this and drawing this horizontal line and finding the intersection of this return period curve and the intersection line, you find what kind of return period of the same event in different worlds. So in the 1.5 degree warming world is about once every 5 years, but as global mean temperature rises, it becomes more likely. So in a 2 degree world is about 1 in 3 years, according to this model and these simulations. And in the 3 degree warmer world, I found that is even more likely. So it's 1 every 1.5 years. So in 3 years, you have probably 2 mortality events looking like a very historic Chicago heat wave in 1995. So another way of looking at exactly the same plots is then to look at what is the mortality level associated with a relatively extreme event. So if I determine or if I define an extreme event being an event that happens once every 30 years, so pretty unlikely for a certain year, and I draw this vertical line at 30-year return period, then I can read off the graph and see, how many deaths are associated with a 1 in 30-year event. So in the 1.5 degree world, that's about 900 deaths for Chicago. 2 degrees world is over 1,000, and 3 degree world is 1,781 deaths. And yeah, I need to remind myself that in these worlds, the only difference is the climate. I haven't looked at whether I've made the assumption that there's no change in the population structure or population density or vulnerability or adaptation or urbanization across these worlds. So any difference in the results here in terms of deaths in a 1 in 30-year heat event is attributed to, global warming. So I looked at all 15 cities in the United States studied in the study. So it's not just only 15 cities in the United States, but anyway, I looked at 15 cities and I looked at the number of deaths associated with a 1 in 30-year events in the 3 degree world. And that's indicated by the size of the outer circle over each city. And I framed the results in another way, such as that if we limited global warming from the current trajectory of 3 degrees down to 1.5 degrees, which is the Paris Agreement's target, the more ambitious one, how many heat-related deaths could be avoided? And that's indicated by the size of the inner circle. And the same for the 2 degrees world. So if we limited global warming from 3 degrees to 2 degrees, then how many heat-related deaths associated with an extreme event could be avoided in the inner circle. And so these are all normalized numbers. If you can see at the bottom, they are deaths per 100,000 people. And they, when we normalize the results by the population of the places, then Miami stands out. The number of deaths at 3 degrees are the largest at 520 per 100,000. And that's likely because generally, I think there are more older people living in Miami than the rest of the cities I studied. So social factors play a role in the impacts of heat and climate change on health. So not just the United States, but another study published in 2018 looked at other places. In fact, I think they looked at 451 locations in 23 countries. These are the places that they could estimate the association or the curve between temperature and mortality. And therefore, they applied those, assuming that those curves don't change again. They applied those to, again, climate scenarios in the future of 1.5, 2 degrees, 3 degrees, up to 4 degrees global mean warming. And the red bars are the changes in heat-related mortality in each of the big region. The first bar is for each region, the first bar is the difference between 2 degrees versus 1.5 degrees. The middle red bar is that between 3 degrees and 1.5 degrees. And the rightmost bar in each region is 4 degrees versus 1.5 degrees. So you can see for most regions in the world, as global mean temperature goes up, more heat-related mortality is expected, according to the models. They also looked at cold-related mortality and how that might change under global warming. And consistently, they find a decrease in cold-related mortality, indicated by the blue bars here. And then they looked at the net change in temperature-related mortality, meaning, if there's an increase in heat deaths and a decrease in cold deaths, what's the net change in deaths associated with temperature? And that's the black dots here. And for a lot of the places, there's still a net change in positive change, so an increase in temperature-related mortality, except for North Europe, East Asia, and Australia, although the net changes are nearly zero for some of the places. Again, this is a study that's based on a lot of assumptions, including no changes in population and demography and the age distribution and vulnerability of people in these places. And looking at closer to where I am, at least, for Bristol, I did a similar thing, following exactly the same methodology published in my paper for the United States, but applying Bristol data, looking at what different levels of warming mean for mortality associated with a 1 in 30 year events for Bristol. So this also includes results from a historical run that shows that that's based on past decade of 2006 to 2015. And in that historical scenario, about 40 deaths were 100,000 people associated with a 1 in 30 year heat event, going up to 1.5 degrees warming globally for Bristol. Then that's 370 deaths, 2 degrees, 410 deaths, and 3 degrees, a lot more, 600 deaths. And I think Bristol's population is 467,000. So if you multiply that with this number and look at the difference between 3 degree warming and 1.5 degree warming, then mitigating climate change to 1.5 degree warming could potentially avoid over 1,000 deaths in Bristol, assuming that nothing else changes. But of course, other things change, right? Like population will change. Whether the population is aging or not will change. A lot of other factors that aren't just the climate will change, but I don't know personally how they may change. So this is a slide given by my colleague Natalie again. She's looking at how population is projected to change in different places in the world. And these are two maps showing the change. I think the left-hand map shows the projected change in a certain shared socioeconomic pathway for up to, I think, 2050, so first half of the century, and then the second one is later than that, so the second half of the century. And for this is just one of 5, I think, shared socio-economic pathways that are proposed in the newest generation of climate kind of scenarios. And these pathways include things like population growth and how sustainable a place is, and urbanization and so on. So according to this map, then up to 2050, a lot of places have an increasing trend in population. That includes Europe, South Asia, and Sub-Saharan Africa. India, in particular, is very red on this map, showing a large increase in population projected under this pathway up until 2050. For this pathway, population kind of levels off, or even the trends decrease in some places in the second half of the century. So Natalie's looking at the combination of changes in future temperature and future relative humidity, and also future population, and therefore what might heat stress mean to different populations in the world in the future. And another thing that needs to be considered when we look at kind of heat health, especially for smaller regions, especially for cities, is urbanization, because there's this phenomenon called the urban heat island effect in a lot of places. That is when an urban area is warmer than the surrounding rural and suburban areas. And the intensity of an urban heat island is often just the temperature difference between an urban and a rural area. So on the left-hand side, here's a map, I think, of August 2003, so the European heat wave, showing W is Wolverhampton, B is Birmingham, C is Coventry, and that's a temperature map. Redder means hotter, and you can see these cities are warmer than the surroundings. And on the right-hand side, also another map for London, taken from another paper, also for August 2003. This is now a north to south transition of across London. And the squares indicate the urban fraction, so how urbanized a place is in London. And central London is very urbanized, so nearly 1. And the other parts are more rural. And you can see that the temperature, that's the triangles on this graph here, are also warmer where, you know, places are more urbanized in London. And these are both from 2003. So I'm going to just mainly quickly talk about the main causes of an urban heat island. Basically, in an urban area, you have a lot of built materials and buildings, and these materials store heat during the day and they release it at night. But, you know, in the surrounding rural area, you don't have these structures that store so much heat. There's also anthropogenic heat sources, such as from traffic, from, you know, energy use in a home, also from industrial processes, and they contribute to heat in the urban area more than the rural area. There's usually also a lack of vegetation in an urban area, and that reduces cooling by evapotranspiration, and therefore is usually warmer in the urban than the rural area. Right, so another study that I did when, you know, in my post in Bristol was to look at how urban heat island effects might change in the future in England. So I studied 10 major cities in England itself. They are shown on the map here. And I used the latest, newest UK climate projections by the Met Office called UKCP18. And what's good about these new projections is that it has a relatively high resolution model that can resolve smaller scale cities. And the boxes on the map here shows the grid size of the regional climate model in UKCP18. And it also includes an urban effects by, so the land surface model has 9 surface types, and one of them being urban. So the map here, the color shows the kind of how urbanized places in this model are, and the deep blue is a higher urban fraction, nearly 1 for many parts of London. So by looking at the temperature difference between, say, inner London and the surrounding area where urban fractions are lower, and using projections up to the future, we can look at how the urban heat island effect might change. So that's what I did. And before I talk about this graph in detail, I just want to emphasize that both urban and rural temperatures are projected to increase in the future. This is just showing the temperature difference, or kind of like the difference in the rates of increase in temperature between a rural and an urban area. But temperatures are all going to are expected or projected to increase in all rural and urban grid cells that I looked at. So I think the main point of this study was that I looked at both the urban heat island effect in the daytime, that's the red line, and at nighttime. So basically nighttime urban temperature minus nighttime rural temperature being the nighttime urban heat island effect. And what's interesting in this study that I found, the results is that I looked at the changes up until 2080, and for I think most of the places, the models are projecting an increase in nighttime urban heat island effect. And for London, I think at the end of 2080 is about 2.8 degrees Celsius. So even though rural and urban areas are both warming, the urban areas are warming faster at night. Therefore, the urban heat island effect is increasing up until 2.8 degrees Celsius in London. And this may have implications on health because nighttime is important for us to recover from exposure to high daytime temperatures. But of course, if there's an increasing nighttime urban heat island effect, that may mean that the urban populations may find it harder to recover to daytime heat load compared to rural residents. But again, all rural and urban places I looked at are projected to warm in the future, and this is under relative high emission scenario. So finally, I want to talk about another piece of work that my colleague Emily Vosper is doing in our group. She's doing a PhD, which I think is really cool. So basically, when I talked about the urban heat island effect and so on, and looking at regional climate models of UK CP18, I think that's 12-kilometer resolution. It's still, coarse if we want to look at the details of what's the difference, an urbanized city is compared to another kind of rural area. And an example is that Bristol is only covered by 1 grid cell if we have a 12-kilometer resolution regional model. So it's important to kind of downscale models, so to look at finer features. And one of the ways of doing that is to actually include more physical processes and features in your model. That includes, smaller scale rivers and mountains and so on, to look at, to include these processes, and then to look at what it means in terms of weather and climate. But this is computationally expensive, and often you can't run a lot of simulations if you have a very high resolution model. Another way is to not include those physical processes in a model, but establish statistical relationships between larger scale climate features and local characteristics in climate. And that's statistical modeling. And Emily is doing that and looking at how statistical downscaling of climate models can improve our understanding of extreme temperature events, for example. So this is another slide that Emily provided me with. So on the left is a 100-kilometer resolution showing the UK, and on the right is 1 kilometer. So you can see a lot more features are included when the resolution increases. And so what she's doing is to use machine learning techniques to kind of work on this statistical downscaling. And the first step she's doing is to look at London and to use a lot of linear regression in the machine learning models to establish the relationship between the larger scale 100-kilometer resolution observations with some very high resolution observations, and then hopefully to test the model and hopefully to also evaluate how this could be used for future climate scenarios. And so to sum up, in developed nations, high temperatures are associated with increased mortality risks. We know that by looking at the temperature mortality curves, where we have data, and usually they are in developed nations. This association is usually non-linear. Throughout history, there were extreme heat events, and the 2003 European heat wave killed 70,000 people, according to the World Health Organization, and human-induced climate change doubled the chance of this heat wave happening. And human-induced climate change also increased the mortality risk by 70% in Paris and 20% in London. Looking into the future, if we look at the United States, up to thousands of annual heat-related deaths can be avoided per US city during an extreme event, and that's defined by a 1 in 30-year event, if we limit global warming to 1.5 degrees above pre-industrial levels. Similarly, using the same technique, looking at Bristol, over 1,000 annual heat deaths can be avoided in Bristol. But of course, these are based on strong assumptions of the temperature mortality relationships don't change in the future, and also other effects such as population change and urbanization and even adaptation don't change in the future. Whereas in reality, these things will change. So I looked at how the urban heat island effect is projected to change in the future, and found that especially for nighttime metric is going to increase in a lot of England cities, and this may exacerbate heat health impacts in England. Researchers in our team are also looking at future heat stress and crossing that over with population changes, and also looking at how we could use machine learning to downscale larger climate features to local characteristics. And finally, I know it's all quite grim to look at heat waves and how they kill people, but I think by looking at it as in this way of whether or how many deaths could be avoided by mitigating climate change and meeting the Paris Agreement goals, it is quite clear that mitigation of climate change is important in terms of at least reducing heat-related health impacts. But I also want to stress that, of course, adaptation is also very important, because even if we go to 1.5 degrees warming globally, there's still projected to be an increase in heat-related mortality if we don't adapt. And even currently, every year there are excess deaths estimated for each heat wave or a lot of the heat waves. So both adaptation and mitigation are important to kind of reduce the future impacts of heat on health. And I think I'm going to stop here. Thank you.
Thanks very much, Eunice. That was really fascinating and really comprehensive as well. And I think as an epidemiologist, you presented a lot of data and visualizations that I'm kind of not used to seeing. So for me, it really sort of highlighted the potential for interdisciplinary collaboration. So it's really, really interesting. We've had one question in the chat from David Carslake. He said, if the baseline for calculating excess mortality is the past 5 years, then do we risk underestimating the mortality impact of heat waves because the baseline is shifting upwards?
Yeah, that's a really good question. I think, yeah, of course, excess deaths are, dependent on what baseline you're looking at. That's completely right. Currently, what Public Health England is doing is not even looking at the past 5 years. They are calculating their baseline based on the non-heat wave days of the same year, and so the baseline changes every year, and I think it's very interesting. I don't think I know the answer, because overestimating means you know what the actual number is, and I don't think we know actually what's the best way of estimating heat depths. So one way of estimating is the excess depths, and you rely on the baseline. The other way is to use the temperature mortality curves and to apply those on observed temperatures in the past summer, and look at what the models tell you according to the known association between temperature and mortality, what the impacts of heat was last summer. But I don't think I know which way is overestimating, if one value is higher than the other, simply because I don't know what's the truth, and I don't think we all know that. But yeah, of course, if you use a moving baseline and it is of the most recent years, then I guess you would the excess depths might be lower than if you compared it to the 1990s, for example. But you could argue that you're comparing it to the current baseline, because things have changed in terms of adaptation and so on. So it might make more sense to compare it to the more recent times.
Great,
Thanks, Eunice. I was wondering if it's worth, just because I'm conscious of time, for those people who do have questions but can't get them in now before they may have to go off to other meetings. Are you happy for people to contact you, or drop you an email? Were you happy to put your last slide up, which had your email on?
Yes, I'm Eunice.Lo at bristol.ac.uk, and I'm especially interested in just like people in other disciplines and who are interested in interdisciplinary research and future collaborations.
Yeah, I think we have some more questions. I just wanted to say that, just in case people are on the way out. So Gemma, if you want to ask the next one, just goodbye.
Yeah, so Claire asks in the chat, why does the MMT vary so much between cities? Is it because of the varying strength of the urban heat island effect?
I think there are a few factors. That's a really good question. So there's indication that if a place is usually quite warm, such as the curve I showed for Phoenix, then the MMT, that's the minimum mortality temperature, is higher because people are used to the warmer climates. So so the curves and the MMT change a lot from a place to another because of the kind of like climates that's the climate zone that the place is in, and also because of the existing population structure and maybe access to healthcare and population density and even awareness of the health impacts of heat, and that's all contributes to differences in the curve, and also what the threshold called MMT is in a place.
Okay, great, thank you. If anyone else has any questions, I think you can put up your hands, or you can ask to let us unmute you, or you can stick it in the chat. I have a question, if I can be cheeky. So I was just wondering whether you're able to break the mortality data down into by like demographic information, so that you can get a bit more of a handle on like who is dying and what kind of underlying health conditions they might have. So I'm particularly interested in pregnant women, and I just wondered whether it was sort of whether those data exist.
In the literature, there have been studies that look at different age groups and how these curves differ, and also gender, and even different periods of time. So before a heatwave plan came into place and afterwards. I don't think I remember a study, but I might be wrong, about pregnant women. But I think if the data exists, and I think it will with the awareness, but you have to probably, for England for example, you have to apply for the data, I think, and then it will be quite interesting to look at. I agree with you. And also, people have looked at similar things by looking at different causes of death as well. So stratifying it to, a certain cause of death rather than just all-cause mortality. So yeah, this can be done relatively easily. If the data exists, and I'll be very interested in what you're interested in.
Okay, great. Yeah, that's good to know.
I just noticed we had another question in the chat from Julia, but it was sent to me privately, so I didn't notice it. Is Julia still here? Julia, if you are there, are you happy to unmute yourself and ask your question yourself? Because it's it was asking what type of human activities are taken into consideration in these models, but I don't know which models these models was referring to at the time. Oh,
yes, yeah, can you hear me? Yes, hi, Eunice. Yeah, I was just wondering, in the predictive model they use, that you showed at the beginning, what are the type of human activity you take consideration when you compare? I thought it was a prediction between, natural world, so with no human activity, and with human activity. So what do you take in consideration? What are those?
So it will be, so those are the extreme events attribution studies. So it will be, it's not human behavior, but kind of in the climate or in the climate system, the amount of greenhouse gases and, for example, air pollution, and those are the anthropogenic sources, but you also, so the human sources in the actual world. And in the natural world, you wouldn't include those, and you would include only natural cycles in the climate system, like solar activity and volcanic eruptions. These are not caused by human beings, and by comparing two different, so it's a factual world which includes both the human emissions and the air pollutants, and also the natural factors, and a counterfactual world that's only the natural factors. Then you compare the probability of a certain extreme event happening in those two worlds, to look at whether human activities increase the frequency or probability or intensity of the event. But so the human activities you include are in terms of the emissions and the pollution and so on.
Okay, thanks. And can I be cheeky? Can I ask something, like a very quick question? You showed the very first slide was like data from 1800 and up to these days, and I guess the technology has changed a lot. When you compare data like a temperature measure between 100 year to today, do you take in consideration the change in technology, how those data were recorded, how is
Yeah. So so we now have like a very high resolution satellite data, and back in the days it's just measurements in that are a lot more sparse. And these are, I didn't make this graph, but there are global temperature data sets from various agencies like NOAA and in the United States, and the Met Office in the UK, and they would have taken into account discrepancy in these kind of measurements as best as they can, I believe.
Okay, thank you so much.
Can I be sneaky and ask a question, please? Just because, unless I can't see chat. No, I don't think there are anyone in chat. I guess I have like a broader view question, having come from geographical background and stuff. It feels like, so I mean, it's a super interesting talk, and there are so many elements of it that are really interesting and like potentially like really useful avenues to go down. But I think one of the things that I find I've always found in geographial stuff, and I guess I still find in quantitative stuff, is that so many of the things that are there are so many things that are different about living in an urban area and a rural area, on top of the fact that there is this very large and demonstrable temperature difference.
Mm-hmm.
is there any way you can think of, because I guess in like an ideal world, you'd want some kind of artificial control or something like that, where you could imagine that they are exposed. There are people who are exposed to the exact same temperature shock without being in the urban heat island bit, or that kind of thing. I guess, yeah, this is a rambling question. In an ideal world, what would be what do you think is the most interesting opportunity for like climate change and health research going forward? That's a different question to the one I started asking, but I think it's a more interesting one.
Oh, in an ideal world, what's an interesting question?
Yeah, what do you think is like a good, what do you think are like the main opportunities or avenues for like future research linking climate change and health? What do you think is there is still to be explored, and what would you be interested in looking at?
I think in an ideal world, really, I'll be interested in perhaps some of the health impacts that I don't know how to measure. Like, so mortality is one thing that you can count, but whether an extreme event caused distress, and therefore like how that links to mental health is one big issue that I think is well-being and mental health being very important, and I personally haven't done work on it but would think that's important. I think in terms of from the climate side, it's also important to look at compound events. So I'm just looking at heat, but what happens if multiple things happen together, multiple extreme events happen together? That's another thing that I personally am interested in, and also some of the more behavioral changes. So a lot of my research is based on the temperature mortality curve that we established with observed data, and we assume that doesn't change in the future, but of course it will change in the future. It changed in the past, but we don't know how it's going to shift. So we had a previous question about the MMT, and even the MMT shift in the past for places, but it's hard to project how that may change, because that's down to not physics equations, but what people might do. And I personally don't know how to do that. But that's another thing that I think would be very interested to look. I'm very interested to look at that.
Yeah, I think that's super interesting. So I know we've spoken about separately a little bit, is how as in you can map very, very well I say very well, you can map with like relatively high precision the forecast changes in heatwave exposure and in extreme temperatures in the UK, but actually the assumption that they will affect everyone within the UK equally, within, as though adaptation or mitigation measures and behavioral changes will be distributed equally across the populations is a pretty strong assumption. Mm-hmm. And so trying to think about the way those intersect, I think is super interesting. I know, we've done bits of work on where heat waves are gonna disproportionately sort of intersect with existing deprivation and stuff like that. And so sort of people will have less capacity to mitigate stuff. But I think that certainly is super interesting. And I think, you're inadvertently on a call with a load of epidemiologists who are really smart at defining, not me, but like these people are really good at defining sort of health outcomes which you might not have thought of. So I think the blue sky thinking, the better in terms of what you'd want to be interested in, and just see how people can parameterize it. And I think the same is true the other way around. Having moved into an epidemiology department, there are lots and lots of epidemiologists who are very interested in climate change related exposures, be they particulate matter or temperature or this kind of stuff, and just aren't particularly aware of how you might go about parameterizing that. And so it feels like a very fruitful possible avenue for collaboration and stuff. We should we'll chat to Dan about it later. But, I'm rambling, so
health inequality is another thing that's very important, and I highlighted last year and this year. So that's also something of policy relevance as well. So that's another thing that I think is super interesting and should be looked at and addressed.
And I think as well, bringing in the social scientists, because what you were talking about there with in terms of how is society's behaviour going to change, and how is that going to impact the models, that would be a really interesting thing to discuss with them as well. So
Yeah.
I think lots of opportunities, and definitely, as Gareth was saying, like it's difficult to know where to start when you're coming from these sort of disparate disciplines on your own. So it's definitely good to chat about these things. Okay, I don't think there are any more questions unless I've missed any. Gareth, do you have anything else?
No, I think that's good for me. Just that we'll put the recording up somewhere on the student health event website, and yeah, we'll be in touch about the next climate change and health seminar.
Mm-hmm. And
but thank you so much, Eunice.
Talk at
yes, that's one, then now there are 8 people left. It's really relevant. Really strong selection pressures on who we offer speaker slots to. Be able to stay for longer than a normal meeting.
So are you planning, how often is this are these talks in the series?
Like every month.
Yeah, I feel like monthly makes sense.
Yeah.
Given that they're quite far reaching and they'll probably end up you could easily imagine that there's long discussions afterwards each time and stuff, but justifying spending more time than that on it in my current contract. But yeah, I think it was a really, really great talk, Eunice. Thank you so much. And for
thanks very much, Eunice. And thanks
definitely for pitching it. Really great.
7 people left.
yeah.
Thanks, guys.
Well, I mean, we're 3 of them.
Yeah.
Yeah. Maybe just cut the recording like 20 minutes ago.
Yeah, maybe I'll stop it now.